Okay. Okay. Sorry for the delay, but we have the same we had the same problems with the internet, so we have changed our classroom, so we have some minutes of delay. So now we can start. In the last lesson, we arrived at this point about the methods to model the multifunctional processes, and in particular we have said that as regards the modeling of multifunctional processes, we have different strategies according to the ISO standard. The first way is to solve this kind of problem by trying to divide the unit process into different to several sub-unit processes in order to find which kind of materials, energy consumption, emissions are correlated with our main product. I remember you that a multifunctional process is a process from which we have not only one product, but from which we have at least two different products, the main product and a byproduct. This secondary product is considered as a byproduct when it has an economic value. If this secondary product doesn't have an economic value, it should be considered as a waste, not a byproduct. Okay, this is the main difference. And in order to divide the environmental impacts between the main product and the byproduct, we have different strategies according to the ISO standard. The first one is the subdivision of unit process in order to find which sub-processes are related to our main product and which sub-processes, sub-unit processes are related instead on the byproduct. But in the last lesson, we have said that this kind of strategy can be applied only in a few cases, because it is not simply to it's not simple to apply in all cases, because for example, in the case of milk production, we have a problem about the subdivision or about the division in subunit processes, for example, the phase of animal husbandry. So in these cases, the other strategy, the other option, according to the ISO standard, is to apply the system expansion approach, for which we have to identify another product in the market that can be substituted by our byproduct. So in this case, we have to calculate the environmental impacts associated to this alternative product in the market, and then this environmental product should be subtracted by the total environmental impact associated to our life cycle. So this is the idea behind the system expansion approach. This approach is the best option for the ISO standard, but also in this case, it is not easy to apply this method in all cases. For example, you can see in this slide an example about the possible application of system expansion approach to cogeneration plant. Cogeneration plant is an industrial plant for energy production, in which we have the production at the same time of electricity and thermal energy and heat. In this case, for example, if our aim is to analyze the environmental impact due to the electricity production, the thermal energy, the heat, is our byproduct of the process. And in this case, we have, for example, if we want to apply the system expansion approach in order to consider the contribution of the byproduct of the thermal energy, of the heat, in this case, we have to calculate the environmental impact associated to the production of the same amount of the thermal energy, but by applying a traditional technology. For example, the production of thermal energy by using a natural gas boiler, for example. So in this case, we have to subtract the environmental impact of the production of 1.5 gigawatt hour of heat obtained from the combustion of natural natural gas, by the total environmental impact due to the cogeneration plant. So this is an example. It's not important for us. Here you can see another example about the system expansion approach, in which you have an example of an agricultural process, in which from this agricultural process we have the production of wheat as the main product, and straw, wheat straw as the byproduct. So also in this case, it's possible to apply the system expansion approach, because wheat straw, for example, it could be used as a fodder for animals. Also in this case, you have the possibility to apply the system expansion approach. Yeah, this is the example for milk production. As we have said in the last lesson. Instead, the other method to model a multifunctional process according to the ISO standard is called as allocation procedure. The allocation procedure is an alternative way to divide the environmental impacts between main product and the byproduct. I repeat, we have the first way is the division of unit process into different sub-unit processes, first approach. Second approach, the application of system expansion approach. Third way is the application of the allocation procedure. The allocation procedure is divided into at least 3 different criteria. Now we'll see how this kind of procedure could be applied in the LCIA. The application is quite easy, and in particular, it is more easy than the system expansion approach. In this case, we have to we can consider an example, okay, to explain the allocation procedure. For example, if we consider the previous example about wheat and straw, okay, the agricultural process for the production of wheat and straw, okay. In this case, for example, we want to apply the allocation procedure, the allocation approach, according to the mass content of these products. The calculation is quite easy for this reason. First of all, we have to calculate the environmental impact due to the agricultural process. For example, if we refer to climate change impact category, we have to calculate the greenhouse gas emissions due to the different agricultural steps in order to produce wheat and straw. Probably we could have different agricultural operations, no, in order for the cultivation of wheat, for the production of wheat and straw. So, for example, we have calculated that from our process we obtained 8,000 kilograms of wheat, 2,000 kilograms of straw, so 8 tons and 2 tons of wheat and straw respectively. So if we want to apply the allocation procedure according to the mass content of the products, the only mathematical operation calculation is to calculate the percentage of the overall impact due to wheat and so due to the straw. This percentage is calculated by considering the ratio between the weight of straw divided by the sum of the weight of straw plus the weight of wheat. Okay, so weight of straw divided by, the weight of wheat divided by weight of wheat plus weight of straw. So in this example, you have 8 tons divided by 10 tons, okay, in this example. So in this case, you obtain 80%, okay? 80% is the final result of the calculation. So if, for example, we have calculated that the greenhouse gas emissions due to the agricultural operations were equal to 10 kilograms of CO2 equivalent, if we want to calculate the exact impact associated to the wheat, we have to multiply 10 kilograms of CO2 equivalent by 80% by 0.8. In this way, 8 kilograms of CO2 equivalent are attributed to the wheat, and 2 kilograms will be attributed to the straw. Okay, this is the calculation if we want to apply the allocation procedure according to the mass content. The weight of the main product divided by the sum of the weight of the main product and the weight of the byproduct. This is the calculation, the only calculation. And with this percentage, we apply this percentage to the overall environmental impact of the process. Okay, this is the calculation. This is one option to apply the allocation procedure. But according to the ISO standard, we have the possibility to calculate this percentage of impact, not considering the mass of the products, but considering, for example, the energy content of the products. So in the case of wheat and straw, the percentage in this case, if we want to apply the economic criteria for the allocation approach, in this case, we have to calculate the ratio between the economic value of 8 tons of wheat divided by the economic value of 8 tons of wheat plus the economic value of 2 tons of straw. So in this case, the ratio is based on the economic values of the products. So in this case, I don't know, for example, we know that 8 tons of wheat, the economic value is equal to, I don't know, 100 euros. And instead, the economic value of 2 tons of straw is equal to 20 euros. The ratio is 100 euros divided by 100 euros plus 20 euros for straw. So 100 divided by 120. Okay. In this way, we can calculate the percentage according to the economic value, and then this percentage is used to divide the environmental impact, the previous 10 kilograms of CO2 equivalent, in order to divide the impact between the main product and the byproduct. Okay. The procedure is the same, but in the first case, it's the mass content, the criteria. In the second case, is the energy, the economic value of the products, the criteria. Then we have the third possibility, the energy content. In this case, we have to calculate the energy content of 8 tons of wheat and the energy content of 2 tons of straw. And so the calculation is the same, okay? Is the same. So about this approach, we have to make some considerations, because this approach is more easy than the system expansion approach, because in that case we have to calculate, we have to find an alternative product in the market for our byproduct, and then we have to calculate the life cycle assessment of the alternative product. In this case, we have only to calculate a percentage. But, for example, the mass approach, the mass criteria could be applied if the product, the main product, and the byproduct have the same use, have the same application, have the same function. For example, in the previous example, wheat and straw, the mass approach, the mass criteria is not very useful because wheat is used as a food. Straw is used as a fodder for animals, or, for example, for energy production. We can use also straw for energy production. So the final use of the final uses of these two products are different. So the mass approach is not the best option in this case. On the other hand, the economic approach, the economic criteria could be better than the mass content, the mass approach, because in this case we have a better representation of the real situation, even if these two products are characterized by different uses. But in this case, about wheat and straw, probably economic value is better than the mass content of the products. As regards the energy content, instead, the energy content could be applied only if the product and the byproduct are both used for energy applications, for energy valorization. In particular, I don't know, if you consider the petrol oil refining process, in this case, from the refining of petrol oil, we have the production of different products, gasoline, diesel, and other fossil fuels. And so in this case, all products are used for energy purposes. And in this case, we can apply the allocation procedure by assuming the energy content as our criteria. But in the case of wheat and straw, also energy content is not the best option for our allocation. Okay. So in that case, probably the economic value is the only way to apply the allocation procedure. Okay, so the choice depends on the types of the products. Okay. Yeah. It's not very important for us. Okay, when no common representative physical parameter, so for example, mass and energy content, can be identified for the different output, another relationship must be found between them. Economic allocation is a good option for this. But when we want to apply the economic criteria for the allocation procedure, we have also in this case a drawback, which is the drawback due to the application of economic approach of the economic value. The main drawback is that the economic values of the products can change during time. Okay, and so the actual percentage that we have calculated by applying the actual energy values of the products probably in the next year or in the future years the economic values could change, and so also the environmental impacts that we have calculated for our main product could change due to the different economic values of the products. Instead, in the other cases for mass and energy content, we don't have this kind of problem because mass and energy content don't change during time. So this could be a drawback. So if we want to use the LCIA results, for example, in order to define a possible policy in a certain field, I don't know, in the energy field, in the other kind of field, we have to consider, and if we want to apply the economic approach, we have to consider this drawback, this problem, and we have to probably, it could be better to carry out different simulation by using different economic values for the main products and the byproducts in order to consider in the future different final results for our life cycle. Okay, this is a not very easy point, but we can try to simplify because when we refer to LCA and when we refer to the modeling of multifunctional processes, we typically in LCA we identify two different approaches. Previously, we have seen how we can divide the environmental impacts between main and byproducts, okay, with different strategies. Now, in this slide, we can see two different families, two different classes of LCA studies: attributional studies and consequential studies. Actually, in 99% of the cases of LCA studies, the LCA studies are attributional studies. Instead, consequential LCA studies are not very used because, as we can try to explain later, this scenario is very complex to apply. It's very complicated to apply. Which is the main difference if we want to understand the difference between the attributional LCA studies and the consequential LCA studies? Which are the main differences? The main difference is about the second column, is reporting the second column of this table. the question to be answered by the LCIA study. In particular, when we have an attributional LCIA study, we can answer to this question: what environmental impact can be attributed to a certain product? On the other hand, when we want to carry out a consequential LCIA study, in this case, we want to answer to a different question. In particular, what are the environmental consequences of consuming the product to be analyzed? Okay. This is the main difference between attributional and consequential LCIA study. And also, the second main difference is that typically in the attributional LCIA studies, we use one of the allocation criteria to model the multifunctional processes. On the other hand, when we have a consequential LCIA study, we use typically the system expansion approach to model the multifunctional processes. At the end, the third difference between attributional and consequential LCIA studies is reported, this last difference is reported in the last column of the table. In particular, as regards how we intend to model the background data. We have said in the previous lessons that in the LCIA we distinguish, we define two different kinds of data. Primary data for the to model the foreground system, and secondary data from database to model the background system. Okay, foreground, background system. Foreground with primary data, data measured by in a company and so on. And on the other hand, secondary data from recognized international databases. Okay, so if we focus the attention on the secondary data, if we want to carry out an attributional LCIA study, we consider for these secondary data average data deriving from obtaining by considering different technologies for that process, by considering different efficiencies. So you in the software, in particular in the database or in the software, you can find average data, for example, for the environmental impact of 1 kilowatt-hour of electricity produced in Italy. Okay, you have an average data, an average input and output data for the production of 1 kilowatt-hour of electricity in Italy. Or, for example, you can find in the software, I don't know, the process about the production of a chemical substance. In that case, you can find input and output data that are an average average data for the production of this kind of chemical compound. I don't know, and so in most cases we use this approach for our LCIA study, the attributional study. In the case of consequential study, instead, we cannot use the average data for modeling input and output data, but we have to consider the so-called marginal processes. Then in the next slide, will try to explain this concept, but it's very complex to understand in a few words. It's very, very difficult to understand, okay? But for us, I repeat, in 99% of the cases, all LCA studies are attributional LCA studies. Consequential, for example, attributional LCA studies can be carried out according to the ISO standard. Consequential LCA studies cannot be carried out by the technical standard. For carrying out a consequential LCA study, we don't have actually an ISO standard, a technical standard. ISO 14044 is referred to attributional LCA study, not to consequential LCA study. But in literature, you can find some studies, some consequential LCA study. You can find some of these kind of studies, okay? We can try to define the, we can try to add some details about these two different cases. For example, in this slide, we can read the overall aim of attributional modeling is to represent a product system in isolation from the rest of the technosphere. The question addressed by attributional LCA can be said to be what environmental impact can be attributed to product to be analyzed, or what environmental impact is product X responsible for. So in this case, in the attributional case, we focus our attention only on the environmental impact due to the production and due to the use of the product. Okay, but this separation is artificial because many, if not most, product systems interact with other product systems through multifunctional processes, meaning that they cannot be described as physical entities in isolation. So instead, as regards consequential, I think that in this case, you can see that consequential modeling was developed to eliminate the weakness inherent in the attributional modeling framework due to the attempt to artificially separate a product from the rest of the economy. Its overall aim is to describe the changes to the economy caused by the introduction of the studied product system, for example, the product system consequence. It aims to answer the question, what are the environmental consequences of consuming the product to be analyzed? This example, I think that it could be interesting to try to have a better idea about the consequential approach. We can read this interesting example. You are a dairy farmer and you are asked to lower the greenhouse gas emissions for the milk that you produce, okay? Firstly, you have to monitor and report the emissions of your system in its current state, and you want to identify environmental hotspots. This kind of analysis is a typical attributional analysis. So in this case, we focus our attention only on the environmental impact due to the production and use of the milk, of our milk, okay? But this milk is considered separated by the rest of the economy, by the rest of the market, okay? We focus only on our processes, our flow diagram. We consider all processes of the life cycle of milk, but we don't have interest in the evaluation of the consequences due to the consumption of this kind of milk, for example, okay? So we can continue to read. feed production is an important hotspot. So we find that feed production is one of the main important, or one of the main important process in the evaluation of greenhouse gas emissions for our milk. Okay, feed production for animals. So replacing a main product like cereals in a cow's diet with appropriate co-products such as wheat middlings is stated to be more environmentally friendly. Okay, this is the scenario. Your neighbor farmer happens to produce wheat grain, and this grain is milled in a local factory. The mill is currently used to make bread, whereas the wheat middlings are fed to pigs in a neighboring village. Okay, this is the scenario. So if you want to feed wheat middlings to your cows, you have to realize that also the pig farmer has to change his feeding strategy. To know if feeding the wheat middlings to your cows really reduces the environmental impacts, you need to include in your calculation the emissions of all the processes that change as a consequence of your decision. In this case, you need to account for the fact that you feed fewer cereals to your cows, but that the pig farmer has to feed more cereals now. He cannot use wheat middlings anymore in this scenario. So in this case, you have an advantage in terms of environmental impacts because you substitute cereals with a byproduct obtained by another farmer. But this farmer has consequences due to your choice. And so his environmental impacts could change due to your choice. And so if you want to consider your product not separated by the rest of the economy, if you want to calculate your environmental impact, you have to consider also the environmental impacts due to the differences, to the changes caused by your decisions. This is the consequential approach. It's very complex approach. Okay, it's not very easy to apply, to understand, and for this reason, ISO standard defines the guidelines only for the attributional LCA studies, not for consequential, because it could be impossible to define exactly the guidelines for this kind of study. Okay, this kind of study, it could be interesting if you are if you want to define a new policy, for example, in order to consider all aspects of your policy, for example. But if you want to analyze the environmental product of a product of a certain company, obviously, in that case, the attributional approach is the best option. It's not useful to apply a consequential approach. Okay. So, but it's important to remember that in the LCA field, we can have a different kind of approaches, different kind of studies. And also, we have said previously that This is the main difference, no? Then we have a second difference. This column is not important for us. The other difference is that typically for attributional LCI study, we consider the allocation procedure to model the multifunctional processes. Instead, is system expansion approach to model in the consequential scenario. The last column, we have said about the average marginal. I think that for attributional, in the attributional LCA study, if we want to model the secondary data for the background system, we use the average processes which reflects the modeling of an average supply chain. This means that a market mix is used. For example, we can read, this could be for the global aluminum market or the electricity market of a nation. The former is composed of a range of bauxite mines with different ore grades and processing facilities that employ different production technologies. And so in the database, we can find a process about the global aluminum, about the aluminum production that is an average. That is an average of different technologies for the production of aluminum. Okay, so the same for electricity. In the case of consequential approach, we cannot apply. We cannot use the average data for I don't know, for the aluminum production, for the production of 1 kilogram of aluminum. But in this case, this average about input and output data for the production, for example, of 1 kilogram of aluminum, is not obtained by the average data for all kind of technologies for the production of aluminum actually used. Okay, but in this case, this average is obtained by considering not only possible suppliers of aluminum, but only marginal suppliers. Do you know the meaning of marginal suppliers in your experience? Marginal suppliers. In the economy, you have in this case marginal suppliers. In a few words, we can define marginal suppliers are those suppliers able to increase or decrease their supply when demand for their product or commodity increases or decreases. This is the definition in a few words of marginal suppliers. I don't know, with an example. With an example, if we consider the aluminum production process, the marginal suppliers could be only suppliers that use technologies that can be increase or decrease its production due to a change in the market demand of aluminum. So you have to consider a marginal supplier only a supplier that uses an actual and not an old technology, because probably only supplier, only a producer of aluminum with a recent technology can change the production rate of aluminum in his industrial plant. But if the technology is an old technology, probably it is difficult for the supplier, for the producer, to change the production rate for aluminum. So it's not very easy to understand, but marginal suppliers include only a category of global suppliers. So only suppliers able to increase their supply when demand for their product increases or decreases. Typically, these suppliers are those which use recent technologies, not old technologies. In the other case, in the attributional LCIA study, instead, we include all suppliers, old and recent technologies, okay? Old and new technologies. So this is the difference. But I repeat, for us, attributional case, attributional study is the most used scenario, is the most used approach. Okay, with the modeling of multifunctional processes, we have ended the first step of LCA, the goal and scope definition. So I repeat that in the goal and scope definition, we have to define the hypothesis of the study, according in particular to the 6 points that we have seen in the scope definition: function of the study, functional unit of the study, system boundaries, cutoff rules, data quality requirements, and modeling of multifunctional processes, okay? We have seen these 6 points, okay? These 6 points are very important, and each LCA practitioner should declare in his report these 6 points and these choices for these 6 points, okay? So if you have the possibility to read in the future an LCI report or a scientific paper about the application of LCA, you will find in all cases, you will find these 6 points, okay? On the other hand, the LCI study is not a good study, okay? The second step is the inventory analysis step. This step is the core of the LCA study. Is the most consuming time step of the LCA study. And in this step, we have to collect input and output data for each unit process of our life cycle. So the first step, I repeat, the first step is to define the flow diagram, so the unit processes of our life cycle, from the extraction of raw materials up to the disposal step of the product. Okay, this is the first step. Okay, the definition of the system boundaries, so the definition of the flow diagram of our life cycle. Then we have to define which input and output data we have to collect for each unit process of our flow diagram. Okay, so for each unit process of our flow diagram, we have to collect this kind of information, this kind of data. Raw material consumption, energy consumption, natural resources consumption, for example, water. And also we have to define the amount of emissions into air, soil, water, the amount of waste is generated by this unit process. And for example, if we have the production of byproducts from this unit process. The collection of this data happens during the inventory analysis step. Okay, in this slide we have said previously we don't find other things. Yeah, we can. Okay, so if we want to define a procedure for the collection, to collect this information, this data, we can try to consider this approach for the collection of data. This method is not very used in a practical situation, in a real situation, but it's a method to collect data, inventory data, mostly from a theoretical point of view, okay, not for practical. So it's not very important, but we can mention this method. According to the method for the collection of input and output data, we can say that typically when we have our flow diagram, so this diagram was made during the definition of the system boundaries of the life cycle. So we have defined all unit processes of our life cycle. Okay. So now we have to start to collect these input and output data for each building block, for each unit process. So from which unit process we can start to collect data? According to this method, typically the starting point is the unit process having the reference flow as product output. The unit process having the reference flow as product output should first be identified, and this is defined as a level 0 process. In this figure, level 0 process is this one. In fact, in this example, we can read that in a study where a window is the reference flow, the level 0 process is the assembly of the window. I remember you that the reference flow, we have seen in the last lesson the definition of a reference flow. In particular, we have seen, for example, when we have defined the definition of functional unit of an LCIA study, we have said that the reference flow is the reference flow is the amount of the product necessary to the production of the unit, of the functional unit. For example, if we have defined, I don't remember if we have seen this example. Yeah, in this case, when we have defined the functional unit, we have seen this kind of example where we have said, for example, for outdoor paints, a possible functional unit useful to consider the quality of the paints, it could be this one. And in this case, we have considered as a functional unit the complete coverage of 1 square meter of printed outdoor wall for 10 years in Germany in a uniform color at 99.9% of opacity. In particular, in this case, this is the functional unit. And then we have to calculate the reference flow, the amount of outdoor paints necessary to obtain the complete coverage of 1 square meter of outdoor wall for 10 years in Germany. And in this slide, we have seen the example for the reference flow. In particular, in this example, we have seen that 0.67 liters of paint A is required to realize the functional unit. Instead, for example, for another product, for the paint B, only 0.15 liters of paint are required to realize the same functional unit. So the reference flow is the amount of the product to realize the functional unit. So when we define the functional unit, in all cases, we have to define also the reference flow associated to the functional unit that we have chosen for our study. So we can now return to our slide. And so in this case, in this example, if we have a study about the LCIA of a window, in this case, the assembly of the window is the unit process having the reference flow, is the unit process having the product output, as we can see in this figure. Okay, from window assembly process, the output of this process will be the window, the final window. Then this window is sent later to the use phase. So the level 0 process in this case is the assembly process of the window. Then, as regards the level 1 instead processes, the processes required to deliver flows that will be physically embodied in the reference flow should then be identified. These are considered as level 1 processes. In the window examples of level 1 processes are the production of glass and the window frame. So here you can see that with the blue color, you have the level 1 processes. So first of all, the idea of this method is that we have to collect, first of all, input and output data for the level 0 process, the window assembly in this example, and then we continue the collection of LCIA of inventory data for the other for the level 1 processes. In this case, level 1 processes are those processes required to deliver flows. And then we can see, for example, other different levels of processes, but for us, probably only the level 2 processes are important, because the level 2 processes are the processes required to deliver flows that perform a supporting function to the level 0 process. for example, not becoming physically embodied in its output. In the window example, examples of level 2 processes are the supply of electricity used in the assembly of the window, or the transportation needed to deliver the flows of the level 1 processes to the level 0 process. Typically, in LCIA studies, the most important processes and the processes for which it's important to collect inventory data are level 0, level 1, and level 2 processes. Then here you can see other kind of processes defined as level 3 and level 4, but typically these processes are not considered in the modeling, in the calculation of the environmental impact of a product. In particular, level 3 processes, for example, are typical examples are administration and marketing processes. So the electricity consumption of the offices for the administrative offices or the marketing offices of the company. These kind of processes are not considered in the life cycle of a product. Also, another family of processes that typically are not considered during the collection of inventory data are the processes about the production and maintenance of the assembly machines. Why the for example, the equipment and the infrastructures used for the life cycle of the product, used for the production of the product, are not considered typically in the LCIA study, and so are not considered in the inventory analysis. The reason is that typically the impact due to the production and maintenance of infrastructures, for example, simply the road, if we have in our life cycle, if we have the transport of such material from a supplier from a company to another company, we have to consider the petrol oil consumed during the transportation. But if we want to consider all inventory data for our process, in theory we have to consider also the environmental impact due to the production of the road, due to the production of the car, due to the production of the truck, due to the production of an equipment, okay? But these environmental impacts typically are characterized by very low values, and so these impacts can be neglected from our analysis, okay? Because their impacts are very low than the other processes. So typically we consider in a life cycle only the level 0, level 1, and the level 2 processes for the collection of inventory data. Breck.
Yes, this is the slide we upload, but when I push it, I cannot.
Okay.
So,
Okay. So tomorrow I will upload the slides. Okay. I don't know the reason.
yes.
Em xuống dùng 8.
Ừ. Chị không biết cái đấy, cái mua picture poster
Được đấy.
không biết cái đấy gì không là ấy.
Đưa chơi đúng không?
Ừ.
Xuống đấy.
Ừ. Xong rồi tí lại thấy có một đường.
Okay, so. Yeah, this is the previous consideration about level 3 and 4 processes. Okay. So yeah, in these slides, this slide, these slides, we can see another possible approach to collect inventory data. In fact, when we have to define the unit processes of our flow diagram, and when we have classify the unit processes according to the I don't know which is.
Next.
Yes. I don't know. One moment, because we have a problem for the reproduction of the slides. I don't know which is the problem. Adesso proprio sì, scomparso del tutto. Sì, non so se ho mosso. Anche perché non so quale poi il cavo.
Nemmeno io non ho la più pallida idea.
Questo è internet. Quindi
Ma loro riescono, niente, non...
No, non so lei che non... You have the possibility to connect with your PC? Ah, okay, so because we,
C'è riuscito, già
okay,
fatto. Ci ho già pensato da sola.
okay, okay, allora okay. We can continue with
Lei
your...
c'ha lo schermo condiviso, quindi...
Okay, okay.
Ok, mamma mia.
Grazie.
Terza aula oggi, eh?
Yeah.
Ma tre.
Okay, sorry for the technical problems, but we can continue. We have said that after the classification of processes into different levels, the following step it could be to define the different quality of each data for the unit processes. In particular, in this slide, you can see that it's possible to identify data with different quality, from very high quality to very low quality. Very high quality is for data directly measured, for example, in a company. So our primary data, very high and high data are data obtained from, I repeat, from the company. So we have, in this case, data, we can refer to this data to primary data. We can read at the end of the slide, often a directly measured flow will not directly refer to the functional unit of the study, but rather as a quantity per unit of time. In this case, the flow needs to be scaled to the functional unit. For example, a typical situation is reported in this slide. We have a unit process for which we have defined, I don't know, the consumption of material X, 1,500 kilograms per year. We have calculated the emission of the amount of emission of nitrogen oxides, 500 kilograms per year, and we have as output we have the product Y, 1,000 kilograms per year. So if our functional unit for this process is 1 kilogram of the output product, in this case, we have to recalculate each input and output data by dividing, obviously, each value by 1,000 kilograms of per year of product of output product. So the final unit process, the final data for our unit process will be in the second figure, no? 0.5 kilograms of nitrogen oxides emissions per 1 kilogram of product of output product, and 1.5 kilograms of material X per 1 kilogram of output product. So this is a typical operation necessary to report each input and output data to the final functional unit. Another situation when we calculate the data, the inventory data, is this one. In particular, In this example, you can see how this problem is typical for when we have an emission into air, soil, or water. Is the same, but typically, if we want to use company reports to evaluate, I don't know, in this case, the emissions, the amount of emissions of copper, typically this value is expressed in terms of milligram per liter, so is expressed in a concentration form. So in this case, we have to convert this data into an amount at the end of the figure per the functional unit considered for the study. So in this case, we have to convert these 0.1 milligrams per liter of emission of copper to an amount of emission of copper expressed in terms of 1 kilograms of output product. So here you can see mathematical operations for to reach the final expression of this kind of output, but it's so not very important. In the following slides, you can see other considerations about the quality of data, but I think that it's important. So here you can see, for example, for if we want to express the data, no, if we want to classify some data not as very high or high quality, but with medium or low quality data, medium or low quality data are data. Yeah, we have a problem with the monitor. Sorry, but if we consider medium or low quality data, in this case, we have to collect this data from databases. And in this slide, you can see some databases that you can find in the commercial CIMAPRO software. And as I have said previously, EcoInvent is the most used database for the European processes. But also here you can see other important database, always for the European context, as for example, AgriFootprint, that is an complete database for feed, food, and biomass products, or other. I repeat, you can find other kind of database. Yeah, I think that here is not very interesting consideration. We can jump this slide. Instead, here you can see the screenshot of a process inside the commercial CIMAPRO software. For example, here you can see the structure of a process inside the CIMAPRO software. In this case, this process is related to cast iron production. Okay, you can see in the first line, no, the name of the process, cast iron production. Okay. Now for us, we can see simply that in each process in the commercial LCIA software, in the first line we have the name of the process, and here at the right, in the column amount and the unit of the first line, Okay, in the first line, you can see amount column and unit column, 1 kilogram. These two cells are referred to the functional unit of this process. So the following data about input and output data are referred to 1 kilogram of cast iron, okay, for the production of 1 kilogram of cast iron. So you in the software you can find a very long list of these processes, and for each process, and each process is made with the same structure. First line is the name of the process. Then you have the functional unit of the process, in this case 1 kilogram. And then in the following lines, you can find inputs and outputs at the end of the figure. In this case, in this example, in the inputs section, you can see the input data used for the construction of this process. In this case, for the production of 1 kilogram of cast iron, it's necessary to use, for example, 0.005 cubic meter of water, a particular water in this case, but it's not important for us in this moment to know which kind of water is used in this process, but 0.05 cubic meter of water. Then you have other input data for this process. For example, I don't know, you have, for example, in this long list, you have the consumption of natural gas, high pressure, 0.001 cubic meter. You have the consumption of oxygen liquid, 0.05 kilograms, and so on, okay? So here you have all input data for this process. At the end also you have the electricity consumption for the production of 1 kilogram of cast iron, in this case 0.42 kilowatt hour of electricity. And then in the following lines you can find, not in this slide, but you could find the outputs, so the emissions and the wastes generated by the production of 1 kilogram of cast iron. So if in your life cycle, when you have defined the system boundaries, when you have defined the unit processes of your flow diagram, and when you have, and if you have, for example, in one part of your flow diagram, you have the consumption for the process, you have the consumption of, I don't know, 10 kilograms of cast iron. In the software, you can choose this process, and by selecting this process, you have the possibility to consider the environmental impacts due to the production of 1 kilogram, and so due to the production of 10 kilograms of cast iron production. In the following, in the next lesson, I don't know, probably I don't know if it was next week or in the other week, with my colleague, you will see the structure of the CIMAPRO software. Okay, so you, I think that you can understand this concept. But for us, in this moment, we can see the structure of a unit process inside the software. So inside the software, each process is characterized by this structure. The first line is the name of the process, and then you have a section for the input data and a section for the output data. Okay. and you have the possibility to create a new process with this structure, or you have the possibility to use a process from the database. Okay, so in your life cycle, you will have some processes, some new processes created by you, and some processes obtained from database. Okay, and then you can collect this information in one life cycle. At this point, I think that it could be useful to see an example. In this here, this is an example. This is a case study about the life cycle assessment of production of soybean oil. Okay, about soybean oil. But it's interesting now only to see how which kind of data are important to collect for this during the inventory analysis. No, if we want to analyze the environmental impacts associated to the life cycle of to the production of soybean oil, we have said that the first step is the definition of the system boundaries, no, of the product. In this case, our system boundaries, our flow diagram is this one. Okay, the first steps are the production of fertilizers, the production of herbicides and insecticides. So for us, in this case, these two first unit processes are related to the production of the materials, no, of the materials. Then the following step, the following unit process is the soybean cultivation process. The following step is the production of soybean oil. The following step is the use phase, and finally you have the waste management step. In particular, in this flow diagram, you can see that for production of soybean oil, you have some additional unit processes about the steam generation useful for production of soybean oil, the generation of electricity, truck transportation of soybean from field to the company, and production of hexane useful for the production of soybean oil. So in this case, in this example, your system boundaries are these. And so in the first step, you have identified the unit processes of your LCA. This is in the first step of LCA, in the goal and scope definition. So here you can see, you can read the definition, no? The first step, the definition of system boundaries. Then you have to define the functional unit of the LCA. In this case, the functional unit, I don't remember, but I think that it is, I don't know, 1 liter probably of soybean oil. I don't remember exactly the functional unit in this case. And then after the definition of the functional unit, in theory, after the definition of the cutoff rules, after the definition of the data quality requirements, after the definition of the method to model multifunctional processes, in this example, we don't have these sections. The following step is the collection of the inventory data, input and output data for each unit process of the system boundaries, okay, of the flow diagram. In this case, here in the soybean cultivation sheet, you can find the input and output data for this first for this first step, soybean cultivation. Okay, in this case, you can find, for example, the input data here. Okay, input data. For input, in this case, as input data, we considered, for example, in this case, 30 kilograms of soybean seeds. In this case, these input and output data are referred to 1,000 kilograms of soybean. So you have to define other inputs, the fertilizer consumption for the production of 1,000 kilograms of soybean. So you have the list of fertilizer. You have the amount of the other chemical substances, herbicides, insecticides, and so on. In this, between the input data, you have also the consumption of diesel, for the agricultural operations in order to produce 1,000 kilograms of soybean. And also between instead the output data, these are the output data for this unit process. Air emissions, CO2, CO, hydrocarbons, and so on, water emissions, nitrogen in water, phosphate in water, and so on. So you have to consider that I don't know in this case, but this data could be primary data if you have the possibility to measure these. For example, consumption of fertilizers, these emissions of this amount of emissions into air or into water. On the other hand, you have the possibility in an LCIA study to obtain input and output data for soybean cultivation by choosing this process from the database. In the database, you have the possibility to have to select the process about the production of 1,000 kilograms of soybean. Okay, and so in that case, you have an average. You have average data, average input and output data to model the production of soybean. Instead, if you use primary data, you have the possibility to model exactly your process, not considering average data, but considering your specific process, okay, about your specific company. But it's not easy to collect this kind of information. It's not easy to collect this kind of data. And it's not easy to collect this kind of data for all processes of your life cycle. In this sheet about soybean oil production, you can see instead the table for input and output data about the production of oil. These input and output data are referred to 1,000 kilograms of soybean oil. In this case, for example, you have the consumption of a chemical substance, the hexane, 3 kilograms per 1,000 kilograms of oil. You have the consumption of steam, electricity. You have the consumption of diesel for soybean transport, and you have in this case only the emission of hexane. So in this way you can collect input and output data for each unit process. So the idea is to find this kind of data, okay, for all processes of your life cycle. Okay, these are the same tables for the other processes of the life cycle. Also, we can start today to see. I prepared a checklist that usually is used by the LCIA practitioner to collect data, input and output data, to model a life cycle by using primary data. Okay, I don't know if you want to start an LCIA study for a certain product. You have to ask input and output data to the company. Okay, but how can which kind of data I can ask to the company? In this file Excel, you have a detail of the most important information and data to ask to the company in order to complete the inventory step of the life cycle. For example, this checklist was made for a generic product. Okay, so for each product, probably it's important to specify some information, but this is obviously it's a generic data sheet for the collection of data. For example, I divided this file into different sheets. In the first sheet, you have the possibility to collect some general information about the company and about the product to be analyzed. In particular, for example, you can find here that it's important to collect information about the product name, obviously. The reference year is important to define. Firstly, it's important to define because primary data should be referred to a specific year. So if we want to analyze a product today, the most recent year to collect data will be 2023. Okay, not 2024, but 2023 is the last year, most recent year. But we have also the possibility to select another year, for example, 2022, 2021, but it's important to define when we want to collect inventory data, it's important to define which year on which year is based on our analysis. Okay. So then, for example, mass of reference unit. So if we want to consider the LCA of a product, I don't know, of a smartphone, it's important to know also the mass of the product of the analysis. The composition is another important information to ask to the company. The composition in so the percentage and weight basis of the different materials of the product. It's important to know the stages of production process in order to define the system boundaries of our life cycle, in order to define the list of unit processes of our life cycle. Then you here you can in the following lines you have some informations about the characteristics of the different stages of production process. In fact, it's important to know, for example, the length the duration of each production cycle. It's important to know the number of products produced for each production cycle. So here you have some different data that are important to collect for our life cycle. For example, it's important also to ask to the company other products produced in the same production cycle. Why? It's important to know if from our production cycle is produced another kind of products different to the main product. It's important because if you have, for example, an equipment, a machinery, and this machinery consumed electricity, and from the use of this machinery, you have the production of not only of my main product, but you have the production of also other kind of products. It's important to know the number of our product and the number produced of the other kind of products in order to divide the the yearly electricity consumption between the product to be analyzed and the other products. So these informations are important to know in order to have the possibility to divide in an accurate way the input and the output data. I repeat, between the main product and the other products, the other possible products. Then in this sheet you can see also that it's important to know for each phase of the production cycle, it's important to know the machineries employed for each phase. Why it's important to know the characteristics of the machineries employed for each phase. It's important because typically when we want to determine for example, energy consumption of machineries, in particular the electricity consumption of the machineries, it's impossible to obtain from the company the exact consumption of electricity for each machinery. Company knows the total electricity consumption of the plant, of the industrial plant, but company does not know the electricity consumption for each machinery. And if we want to know instead the exact amount of electricity consumption for each machinery, the only way is to calculate the electricity consumption of each machinery by knowing which informations, by knowing the electric power of each machinery and the hours of operation for each machinery. By multiplying the electric power in watt by the number of hours of operation, we can calculate the electricity consumption, the kilowatt hour of electricity consumption. So for calculate, if we want to calculate the electricity consumption of each machinery, we have to know the electric power of each machinery and the number of hours of operation of each machinery. By multiplying these two data, we can calculate the electricity consumption of each machinery. So for us, when we want to collect data, it's important to have exact. It's important to have all these kind of details for each machinery. Okay, so I think that for today it's all. We'll finish to see these sheets on Friday. Okay. Yes.
Hello, I'm sorry, Professor. I have a question. I'm an Erasmus student from Ukraine, and I'm just arrived. Sorry, I couldn't visit earlier your lessons because I wasn't in Italy and in Viterbo. So I would like to know how exam will be and if it's a problem that I will join Zoom often because I live in Viterbo, not in Civitavecchia, and I have another lesson in this day. So
No, it's not a problem for me.
okay, cool.
The exam is this subject is divided into two parts. Okay.
Okay.
The first part is this one, 3 credits. 4 credits. And the second part will be taught by Professor Marco Marconi. Also, the second part is of 4 credits. And the exam, the final exam, is will be about both parts. I think 2 questions about the first part and 2 questions about the second part of Professor.
Okay, it's oral exam, right?
Okay. See, yeah. The exam is oral. Only oral.
And one more question, sorry. I would like to know if I can just pass one part, for example, your part, because I need only 4 credits for my Ukrainian system and I don't need 8 all. So Angela just in international office, she just wrote me this subject for one part, 4 credits.
Okay.
Is it fine?
Yeah.
Oh, perfect.
It's okay. For me, it's not a problem. So for me, it's okay.
Okay, amazing. So I can join online and when exam is, I will go to Civitavecchia to pass it, right?
Okay, perfect.
Okay, thank you so much for answer. It's clear. Thank you. Have a nice day.
Thank you. Bye-bye.
Bye.